Okay, so as we approach that problem number 10, yes, I know that is a doozy. I do believe that that is in your textbook, and I think it's in the end of the chapter problem. So it's one of those that it's believed that this is the appropriate level for high school students. But that's why we're going through this together, because it is such a difficult problem. So talking about the energy used for the Apollo lunar missions was supplied by the reaction below. Okay. So when you see this, the equation is partially balanced for that, and maybe it's totally balanced. So I probably should have started that up here rather than wasting time writing this down. So I'm just going to hit pause for just a moment. Okay, so one of the things I've tried to do was shorten this problem up rather than going through each and every step. Here is your equation, which was balanced if I have interpreted that correctly. Let's see here. So this was given. We've got a 2 there. Let's see here. And then a 3 here. And then a 6 and an 8. Okay. So one of the things that I had done is a lot of you students were asking, these are in kilograms. Yes, change them to grams. So 1,200 kilograms gives you 1,200,000 grams of this compound. 1,000 grams gives you 1 million grams of this compound. And then 4,500 kilograms gives you 4.5 million grams of this compound. So that's what the orange numbers are. So we said this is a way for you to possibly keep track or check to see if we're on the right track, which a lot of you probably are or were or will be. Okay, so then what hopefully makes sense for this, these purple numbers then is the molar mass or grams per mole for this compound. 2 nitrogens and 4 hydrogens gives you 32. All of this compound here gives you 60.12, and then 2 nitrogens and 4 oxygens gives you approximately 92.02 grams per mole. All right, so then dividing this number into this one, this number into this one, and this number into this one, then gives you your moles of each substance, okay? Then, this is where you can say you start playing your battleship, if you want to call it that, to where what I think perhaps maybe makes the most sense, and I perhaps didn't point it out this way, is let's call this substance A, this one substance B, then this one substance C. So what you're going to do then is convert moles of A into moles of B and moles of C, and then that will tell you how much of that substance is required. Then you have to pick one of these two, convert to moles of A to see how much of that is required. Okay, so then we'll just go ahead and take this 37,494, and again that is from dividing 32.06 into 1,200,000. Okay, so upon doing that, okay, 37,429, I guess is what it is. I have this worked out on the back side of this sheet here. 37,429 moles. It's, say, substance A, but it's probably better to write as N2H4. So here's where our battleship part comes in, if you want to call it that. We're going to convert moles of A to moles of B. Okay, so upon doing that, for every mole of N2H4, we get a mole of, like I said, I think in the book it calls this dimethyl nitrazine or something like that, but we know what we're referring to, so I'm just going to put dimethyl nitrazine for this compound. We know what it is because we're making reference to that here. Okay, so here is our mole to mole ratio. So then what we're going to need to do is go ahead and make that calculation by going back to our balanced chemical equation. There's a 2 down here. Upon doing that, you get 18,624.91. moles of this DMZ or DMN is REQ. Okay? Well, we needed 18,000 and we only had 16,000. So that might be our limiting reactant, okay? Because we're a little bit short, but this is maybe interpreting which one's going to run out first rather than having a clear-cut answer on what's your limiting reactant. Then we repeat this process by taking 37,429 moles of N2H4. Okay, and we're going to convert it to moles of C, or N2O4. For every mole of N2H4, get a mole of N2O4. Going back to our balanced chemical equation, a 2 down here, a 3 here, and then multiplying that out gives us approximately 55,847. Okay, 0.73 moles of N2O4 is REQ. Okay, well, let's look at what we have. We need 55,000. We've only got 48,000. Okay, so maybe that is our limiting reactant. So then the last thing we need to do is convert one of these two substances into letter A. So in this case, I think we'll just go ahead and take letter C, convert that to substance A. So therefore, we've got 48,000, okay, 902, and let's see here. I didn't put decimal places. I got them on this paper, but I didn't put it on here, but that's not going to drastically change your answer. Mole of N2O4. We're going to convert moles of C to moles of A now. So here's our mole ratio, mole of N2O4. We get a mole of N2H4. Going back to our equation, we need a 3, what it looks like, on the bottom. We need a 2 up there. Okay, so upon looking at that, it says 32,601, 0.61 moles of N2H4 is REQ. Okay, so then when we look back at this, we needed 32,000. We had 37,000 to start with. So this is not our limiting reactant. These two were short, but it's where we want to make the discrepancy here. Okay, let's look at what we actually need. So for DMN, we need 18,624. Okay, so you could subtract those two, or we could say 55,847 and subtract those two. So then upon doing this, okay, it looks to me like this is only 2,000 moles short, where this is actually about 6,000 to 7,000 moles short. We could double check that. Let's see here. With our calculator, 18,624 minus 16,633. That gives us 1991. We're short. But then when we subtract these two, 55,847 minus 48,902. Here we get 6945. We're way too short with this substance. So therefore, this makes your limiting reactant or this compound right here is our limiting reactant. So then you don't have to reinvent the wheel. We don't have to start with this number since we've already converted that to moles, which looks like we've done that since we did that right here, 55,847, okay, which was how much was required. I'm sorry. Yes, you got to make sure that you begin with what you actually had. So 48,902 moles of this substance. You convert that to kilograms of water, and you take 48,902 times 8 times 18.02, then divide that by 3. And does it ask for how much water in kilograms was put into the atmosphere then? So upon doing that, you're going to have to divide that by 1,000 then, and 2,349.91 kilograms of H2O. Okay? Now, rather than going through each and every step, we tried to shorten this because this is already 11 minutes. So to do a summary of this, these orange numbers is the grams that you have. These purple numbers is the molar mass of each substance. This number here and here and here is how much you actually had. This is playing your battleship by converting moles of A to letters B and C. And that's what we're doing. Letter A to B, A to C, and this one's converting letter C to A then. So then what we see happening is we're by far more of a discrepancy short with this compound, so that therefore this is your limiting reactant, therefore giving you approximately 2,350 kilograms of water released into the atmosphere. Okay? We try to make that as short and concise as possible, so hopefully that makes sense. And I know this is difficult, and for those of you who are constantly working, plugging away at this, if you have questions, just continue to please ask and keep up the good work. We will catch up to you next time.